Welcome. In this lesson, we're going to start talking about the periodic table and some of the basics of its structure and organization. For this lesson, along with your notes that you should be following along with, you might want to have out your copy of the periodic table so you can follow along and look at some of its characteristics. For as long as we've known about elements, scientists have tried to organize and characterize the elements in a more organized and easily accessible fashion. And one of the first people to do this successfully was Dmitry Mendeleev, and he developed the first table of the elements. And he arranged everything in order of increasing atomic mass, and he placed the elements in groups that had similar chemical properties. So here we have this group with lithium, sodium, potassium, copper. All of them had similar reactions when they were placed in water. So he organized them that way. And he's often thought of as sort of the father of the modern periodic table. Henry Moseley also contributed a great deal to the periodic table, and he decided to rearrange the table a little bit to base the table on atomic number, or number of protons, instead of the atomic mass, which we know can vary quite a bit. And he also wrote this periodic law that says the properties of elements are periodic functions of their atomic numbers. So when we talk about things having periodic functions or periodicity, it just means something that happens regularly. So you might have heard of periodicals, which are things like magazines. They're going to come once a week or once a month. Seasons are also periodic, right? We have winter, then spring, then summer, then fall, and it keeps repeating over and over again. And we'll see similar patterns in our periodic table where we'll have trends that repeat as we move across the periodic table in the different rows. In the structure of the periodic table, we have it organized and we call different rows and columns different things. So first we have our periods, and these are going to be the horizontal rows 1 through 7, right? So if we look at the side of our periodic table, we see these numbers. And these are just the period numbers, the beginning of each row. So we go from 1 to 7. And elements in the same period have the same number of occupied principal energy levels for their electrons, and elements in the same period, their valence electrons are all in the same principal energy level. So all of the elements in period 2 have valence electrons in n equals 2. So they're organized also by their valence electrons. We can also look at the vertical columns, and these are called groups, and they're labeled with numbers 1 through 18, and they're right at the top of each column of our table. And for some of the groups, for 1, 2, and then 13 through 18, every element in the group has the same number of valence electrons. And because of that, they tend to have similar chemical properties because the valence electrons are the ones that are going to be involved most in chemical reactions. We also like to organize our elements in terms of their physical properties. And physical properties describes the characteristics of elements that don't change the identity of the element. So a lot of physical properties are shown in Table S, and they include things like melting point, boiling point, and density. So here's an example from Table S. We have atomic number 2 for helium. We have melting point, boiling point, and density. And these are all things that we can use to classify and identify our different elements. We can also classify our elements in a couple of different categories, like metals, metalloids, and nonmetals. So metals have a lot of characteristics that are similar. So they tend to be solid at room temperature. They tend to have luster, they're very shiny. They have conductivity, so they can transfer heat and electrons through them in their material. They're malleable, which means we can roll them or hammer them and change their shape and get them into thin sheets. We can also draw them into a wire, which is known as ductility. And they have low energy of ionization and low electronegativity. And we'll talk more about what exactly that means in a future lesson. They also tend to be electron donors, or they give up electrons to form positive ions. And on the periodic table, they tend to be over on the left-hand side. So everything over here will be classified as a metal. And some examples are sodium, right, which is right here, iron over here, and mercury right here. Mercury is a little bit unusual in that it's a liquid at room temperature, where most of the metals are going to be solids. Inside the metals, we have a subgroup called transition metals, and these are going to be in groups 3 through 12. So right here, smack dab in the middle of the periodic table, are our transition metals. And again, they're typically hard solids, and they have high melting points. You have to put a lot of heat in to get them to melt, except for mercury again, which is already a liquid. These are really interesting elements in that when they form ions, they appear colored in solution. So we love to use these types of metals for photography and chemistry labs because we get these really pretty colors. And they can often form differently charged ions. So they might be able to lose 1 electron and be stable, or they can lose 2 electrons and be stable like copper. So we'll have different forms. So the transition metals are very interesting elements because they have a lot of cool properties. And here's an example of different copper compounds in solution. So they have these beautiful blue and green colors, which we don't see in other metals. Our next type of element is going to be metalloids or semimetals. And we find these on the periodic table. You'll notice that there is a thick, dark line on your periodic table that sort of zigzags through over here. And any element along this staircase type shape or step line is going to be considered a metalloid. Right? And these are going to be right in the middle of our metals and what we refer to as our nonmetals, which we'll talk about next. Metalloid properties, because they're sandwiched between metals and nonmetals, tend to have properties that are between those of metals and nonmetals. So they form bonds that are partially ionic, so they can kind of lose electrons, and partially covalent, they kind of share electrons. They are semiconductors usually, so they can conduct some heat and electricity, but not as well as metals. So they're kind of right in the middle between our metals and our nonmetals. And here's a list of them. Right, but if you remember that they fall along this staircase or step line, you definitely don't need to memorize that. So boron, silicon, germanium, arsenic, antimony, and tellurium. Another group where we can categorize our elements is in nonmetals. And these are going to be on the right side of the periodic table on the other side of that step line. And these have properties of being gases, they can be solids, or they can be network solids, which we'll talk about later. In the solid phase, they tend to be brittle and they lack luster, so they're not very shiny, which is very different than a metal. They're unable to conduct heat and electricity. They have high ionization energies, and they're highly electronegative. Again, we'll talk about what those terms mean in a little bit. And they tend to act as electron acceptors. So they form negative ions by taking on electrons, which is the exact opposite of the metals, which tend to lose electrons. So some examples of this is sulfur, and you can see that it's a brittle solid. It just forms these sort of powders. Phosphorus, and this is bromine, which is a liquid at room temperature. Our last major type of group is the noble gases, and this is group 18. So we're over here looking just at this final row or final column of the periodic table. And we don't really consider these to be nonmetals because they don't share the same properties of nonmetals. And the noble gases tend to be non-reactive, and they have a completely filled outer valence shell. So they're pretty happy with their full valence shell, so they don't lose electrons or gain electrons or share electrons with anyone. And this means that most of them have 8 valence electrons. Helium has 2. And they don't really form compounds unless we're under really extreme pressure and temperature conditions. So because they don't really interact with anything and they don't gain or lose electrons or form bonds, they were given the name noble gases. So noble people, right, would not come and mingle with the commoners. So that's where the noble gas name came from. Sometimes they're also called inert gases. Another type of phenomenon we see with our elements is something called allotropes. And these are when nonmetals exist in 2 or more forms that are in the same phase, right? And a phase is going to be solid, liquid, or gas. And in a gas example here is oxygen. It can form a compound with 2 oxygen atoms, O2, or 3 oxygen atoms, which is ozone. So oxygen gas is what we breathe. Ozone gas is something a little bit different. But these are considered allotropes of each other because they're the same element in the same phase, but they're slightly different connectivities there. And allotropes will have different physical and chemical properties. O2 and O3 react completely differently in the atmosphere with other compounds. Another example is carbon allotropes, and this one you might be familiar with. So we can have graphite, which is found in a pencil, and it's all made of carbon. It's just carbon atoms arranged in a specific way. Or we can have a diamond, right, which is very, very different in terms of physical appearance and also in terms of hardness and properties. But again, it's just carbon atoms in there, arranged in a particular way. We also have this neat molecule called Buckminster fullerene, which is 60 carbon atoms arranged in this sphere structure that looks kind of like a soccer ball, right? Again, it's just carbon, but it's arranged in a very particular way that gives it a different shape than we would see in a diamond and different properties. So allotropes have, right, the same element composition, but they exist in slightly different connectivities that give them different properties. We can also think about the states of the elements, right? Solid, liquid, or gas as a way to characterize them. And at standard temperature and pressure, which is our normal atmospheric pressure and about room temperature, most elements are solid. So if we look at this periodic table down here, the yellow is solid, and most of the periodic table is yellow. We do have a couple of exceptions in terms of liquids. Bromine and mercury in blue here are in the liquid phase at room temperature. And then we also have a bunch of gases. So H2, N2, O2, F2, and Cl2 all exist as gases, and so do all of the noble gases, which is another reason that they're called noble gases. Okay, so that was our introduction to the periodic table, and you should be able to identify the location of all of these different metals, metalloids, nonmetals, and noble gases on your periodic table. You should be able to recognize and define what a period is, and you should be able to define what the groups are and recognize them on the periodic table so we can use them. Good job today. See you next time.